Hello and welcome to Empowered Learning. This particular video will be about related rates. And so what related rates is about is word problems that use implicit differentiation. So that means we're characterizing or we're modeling something to where it has to be modeled by several different variables, and all of those variables are interpreted as being functions of another variable that may either be explicitly or implicitly stated throughout the problem. And so our goal here is to get used to what implicit differentiation looks like in a basic word problem. Um, and then from that point, see a few problems where we actually have this sort of setup and see how we actually attack it. So I want to start off um, just by taking some steps that we can take to try to solve these word problems. Much of this will be uh, like what you hear all the time whenever you are in math courses and they say, hey, let's figure out how to do a word problem here. Of course, you hear stuff like, hey, make sure that you can draw it, define your variables, state your equations, that sort of thing. So a lot of this is going to be the same. What's going to be different is how we employ the implicit differentiation and everything. So the suggestions for related rates problems, first thing that we want to do is sketch a figure or graph. And of course, this helps us get an idea of how everything is related. We also want to identify variables. And of course, that's important because we need to know what it is that we're solving for before we solve for it. Okay. Also, we want to make sure that in identifying those variables, we want to include the rates that are given and the rates that need to be found. Okay. So in addition to, let's say, x and y, we may have some variables that may be the derivative of x or the derivative of y with respect to some variable. So we need to state that as well. We also want to express all given rates and rates to be found as a derivative with respect to the correct variable. So let's say, for instance, if we have variables x, y, and w in an equation, and all those variables are related to each other by a time variable, then of course, although it may not be explicitly stated in the equation or problem, we need to make sure that all of our derivatives are with respect to t, where t represents time. All right, so after that, number 4, we want to find an equation connecting all the variables identified in step 2. So that's how we model everything. And then, of course, we want to take the derivative of both sides of that equation implicitly. Of course, that means utilizing the chain rule. And then finally, what we want to do is solve for the derivative that will give the unknown rate. Okay. And so those are the steps that we'll take. In the first few problems that we'll see, what we will do is just kind of look at a bare bones problem where we're just plugging in the information, taking the derivative via implicit differentiation and getting the corresponding rate that we're looking for. As we move on, we'll have other problems to where we will see that we have a little more meat around it and we'll have to interpret some things. So, but hopefully this will help you sort of get an idea of how to approach these types of problems. All right, so our first problem here, we want to assume that all the variables are implicit functions of time t, and we want to find the indicated rate. So we have our equation here, and of course it looks like our equation isn't a function. We're given this rate, and we're given a specific value of x and y, and what we want to do is find out the derivative of y with respect to t. So the first thing that we want to do is take the derivative of both sides of this equation with respect to t. So let's go ahead and do that now. So we have d over dt. This will be x squared plus 2y squared plus 2y. And on the other side, we'll have 61. And so since t does not match any of these variables here, we're assuming that x is a function of t. We're assuming that y is also a function of t. So we'll be employing the chain rule in all these terms whenever we take the derivative of it. So the derivative of x squared with respect to x is just 2x times the derivative of x with respect to t is just dx over dt. The derivative of 2y squared with respect to y is just 4y times derivative of y with respect to t. Okay, and of course here we know that what we're looking for here is dy over dt, because that's what was asked for here. For the next term rather, we have 2y. The derivative of 2y with respect to y is just 2. And that should be plus there. Should be 2 times dy over dt. And then, of course, the derivative of any constant is 0. So now that we know this information, we can now go ahead and substitute in what x and y and dx over dt is. So if we code do this, this will be 2 times 7 times dx over dt is 5 plus 4 times y, which is negative 3, times dy over dt is what we're solving for, plus 2 times dy over dt, again, is what we're solving for, and that equals 0. So once we do all that, it's just a matter of number crunching here. So we have 2 times 5 is 10, 10 times 7 is 70. So we have 70 here plus, and we have 4 times 3 is a negative 12. Negative 12 dy over dt plus 2 dy dt is going to be a negative 10 dy dt. So we'll go ahead and make that minus 10 dy over dt equals 0. And then from there, we know that 70 has to be equal to 10 times dy over dt. Yeah. So make sure that that's t and not x. And then, of course, if we divide both sides by 10, we see that our final answer is dy over dt is equal to 7. So our rate of change for what we see here is just 7. All right, so for our next problem, we see that we have a problem where a retail store is trying to keep track of the weekly sales based upon the amount of money they pump into advertising. And so sales, as we see it here, is a function of x, and x is represents the cost, and both s and x are in dollars, and they're related by this following function here. Okay, we see that we have current weekly advertising of $1,000. These costs are increasing at a rate of $200 per week, and we want to find the current rate of change of sales. Okay, and notice here that we said that we know that x is assumed to be a function of t, because all of this is related to measuring things weekly. Okay, so it is implied that we know that s is a function of t, and that x is also a function of t, even though it's not explicitly stated here in our equation. Okay, so first thing that we need to do is, based upon the information, figure out what our variables are going to be and what it is that we need to solve for and what that looks like. So first, we know that our currently weekly advertising cost, which we know is x, is 1,000. So we know here that x is equal to 1,000 for that snapshot in time. We know that the costs are increasing at a rate of $200 per week. So that's a rate, and of course that's like a derivative. So we know that dx over dt is going to be equal to $200 a week. Okay? And so based upon knowing this information, what we want to do now is find the current rate of change of sales. So said explicitly, we want to know what is the rate of change of S with respect to T. Okay, because T is going to be time that is measured in weeks. So this is the information that we need to know. So the first thing that we need to do is look at our equation and take the derivative of both sides of our equation with respect to T. So I'm just going to rename this just S to make this simple. So we're going to say S, this is d over dt on this side, and here this is d over dt, and we are going to take the derivative of the right side here. Okay, so for this side here, of course, what's inside here is S, so this is just ds over dt, and this is exactly what it is that we're trying to find. So whatever it is that we put here on the right side, and of course plugging in our dx over dt and our x at the right time, we'll get a number. So the derivative of a constant, regardless of what variable you take the derivative with respect to, is 0. And then for the next term, we ignore the 20,000, and then we take the derivative of e raised to the negative 0.0001 x. And so since this is a composition function, we're going to be using the chain rule. So chain rule says take the derivative of the outside function, and the outside function is e to the blah, where blah is all this negative 0.0001 x. So the derivative of e to the blah is just e to the blah times, now we need to take the derivative of the inside function, which is the negative 0.0001 x, and we need to take the derivative of that with respect to t. And of course, the derivative of all of that is just going to be the constant, the 0.0001. Okay? And so now from here, we now need to take the derivative of this again, because if you notice here, this is actually a composition function within itself. Okay, so it's not enough just to do what we did here. We would have to go a little further and actually say, well, this is the same as this times dx over dt. Okay, so that's us employing the chain rule. So the chain rule is employed the first time by realizing that e raised to the blah is the outside function, and negative 0.0001 x is the inside function. But within that, we also recognize that x is a function of t, so the negative 0.001 x of t is acting like a composition function within itself. So that's why we have to take and do the chain rule again to what the exponent is. Okay. So in doing that, a simple way to think about it, and I'll just kind of get rid of this to kind of do it again to make sure that this is clear. The variables do not match. So here we have to act as if we're taking the derivative of this negative 0.0001 x as if we're taking it with respect to t. And of course, that part on its own is just this. But then after that, x is a composition function within itself. So we have to do dx over dt. So that's how we come up with that. So scrolling down now, we're going to go ahead and fill in everything. So when x is equal to 1,000 and dx over dt is equal to 200, we know that ds over dt, which is the change in weekly sales, It's going to be the minus 20,000 e raised to the 0.000, and now instead of 0001 and instead of x, we're going to put 1,000 in there. And then this is 0.0001 times, now the dx over dt, we know that that's 200. And so now it's just a matter of calculating all this. So we know that negative 0.0001 is the same as 1/10,000th, or 1 divided by 10,000. And so 1,000 times 1 over 10,000 is just 0.1. So we know here that our exponent, all this is just going to be 0.1 at the end of the day. Okay. We also know that a negative times a negative is a positive. And so we'll go ahead and say that this is going to be positive. So go ahead and take care of that. Again, we got 20,000 times 0.0001, which is the same as saying 20,000 times 1 over 10,000, which is just 2. And then we have the 2 times the 200 that we see here. And we've already said that this was just going to be negative 0.1. And so we end up getting 400 e raised to the negative 0.1. And so from there, we'll go ahead and calculate what that is. All right, and so here we see that this turns out to be about $361.93 per week. And so we're saying at this snapshot in time, if we're currently investing $1,000 a week in advertising, and we know that the costs are going to increase by $200 a week, then we know that the current change in the amount of money in sales that we're getting per week at that particular moment is going to be $361.93 per week at that moment. And so if we kind of look at and think of this critically, this could be a good thing or a bad thing. It really just depends upon what kind of business we're in. Okay. Now, if we're in the business of, let's say, making microchips, then this $361.93 a week may not be enough to support that business, being that for a lot of those semiconductor chips, to make the mask, it takes about $1 million per mask. And of course, it takes a couple of those masks to actually develop those devices there. So, of course, the $361.93 wouldn't be enough. But let's say if we are, and I'm exaggerating here, but let's say we have a lemonade stand on the corner, and we're investing $1,000 in the advertising, and we're making an increase of $361.93 a week there, then our business is booming at that point, especially if we're selling lemonade, for like $5 a cup, and it's only costing us, let's say like 20, 30 cents to make it. So, times are good. So, we're just talking about getting an answer here, but of course, in all these problems, we want to think about what that answer means and how we can interpret that in our own daily lives as well. So let's go ahead and move on to the next example. All right, so for our next example, we have a spherical balloon that is inflating with helium at a rate of 80 times pi cubic feet per minute. And we want to know how fast the balloon's radius is increasing at the instant the radius is at 2 feet. And we also want to know what is how fast is the surface area increasing. So if we're looking here, we have some helium balloon, and of course pumping air into it, hot air into it. And we know that for that balloon, of course, as it inflates, the radius of it is going to inflate as well, or get larger as well. Okay? And so what we're trying to do is take a snapshot in time and say, all right, well, we know how fast volume is increasing in the helium balloon. And we also know at 2 feet, when the radius is 2 feet, we have that measurement there. So what we're trying to figure out is what is the surface area, as well as how fast is that radius increasing. And so we're given here what the volume of a sphere is, and also what surface area is. So we'll take the first question first, which is how fast is the balloon radius increasing at the instant that the radius is 2 feet. So low-hanging fruit here, we know that if we let r be our radius, then r is going to be 2 if everything is measured in feet. We also know radius increasing is a buzzword to let us know that we're talking about derivatives. So this would be dr over dt, or the rate of change of radius with respect to time, which is in minutes in this case. That is what we're trying to find out. Okay. So now what we're going to do is take our volume equation, since we are already given the rate in which the volume is increasing, and use that information to help us find out how fast the radius is increasing. And so here, since we know what the rate of volume is, we're going to call this dV over dt. Okay. So now if we take the derivative of both sides of this equation, we'll have d over dt of v times, we'll ignore the constant there, 4/3 pi, and we'll take the derivative with respect to t of just r cubed. Of course, on the left side, we just have dv over dt, which we know is this 80 pi cubic feet per minute. And we also know that taking the derivative of r cubed with respect to t will require us doing the chain rule. So the derivative of r cubed with respect to r would just be 3r squared times the derivative of the inside function r with respect to t is just dr over dt. And of course, from there, we know that dv over dt is 80 pi cubic feet per minute. Here we can reduce these 3's to 1 here, so we got that. And what we'll have left here is 4 pi r squared times dr over dt. And of course, dr over dt is what we're trying to solve for. Our value for r here is 2. So in place of this r here, we could put a 2 instead. So let's go ahead and do that. So we have here 2 squared, which ends up just being 4. So now we have 80 pi is equal to 16 pi times dr over dt. Let's go ahead and make some room here. And so now all we have to do is divide both sides by 16 pi. That's dr over dt. Of course, the pi is reduced to 1. And of course, 80 divided by 16 will give us 5. And of course, this will be feet per minute, because dr over dt is radius, which is in feet, and time, which is in minutes. And of course, we saw that earlier in the problem up here, where our time here was in minutes. So we know what the rate of, we know the rate at which the radius is increasing. So now let's continue on and figure out how fast is our surface area increasing. So now we're going to use this equation. So we'll call this our part A, this is our part B. So we'll take the derivative with respect to t of both sides of this equation. And since we have that constant 4 pi that we can ignore, we'll go ahead and do that, and then just take the derivative of the r squared part. Okay, so here we know that this is just ds over dt. On the right side, 4 pi. And using the chain rule here, we know that the derivative of r squared is just 2r times dr over dt. And of course, what we're trying to find out here is how fast the surface area is increasing. And the information that we have is what r is, which is 2 feet from what we saw earlier. And we also have what dr over dt is now, which is 5 feet per minute. So we can now go and substitute all this in. So let's say when r is equal to 2 and dr over dt is equal to 5. Come here and we'll say that ds over dt is equal to 4 pi times 2 times r, which is another 2, times dr over dt, which is 5. And of course, all we got to do is multiply all that together. So we have 2 times 2 is 4, 4 times 5 is 20, 20 times 4 is 80. So we end up having 80 pi, and surface area here, so this should be in feet squared, or square feet per minute. So surface area is area, and the rate is area over time. All right, so for our next example, we see we have a 25-foot ladder that's leaning against the house when its base starts to slide away. And by the time the base is 24 feet from the house, meaning the distance from here to, let's say, here. That didn't quite turn out the way I wanted it to, so let's look at that again. So here, basically saying from here to here, at the snapshot in time where there's 24 feet, the base is moving away, meaning that the speed in which the ladder is going in that direction is 7 feet per second. So we look at our model here, and one of the things that I want to call to your attention is all the prep work that I've done here. And so we see that this ladder, wall, and floor sort of models a right triangle where we can utilize Pythagoras theorem. So we see here that at this snapshot in time, x, which is going to be the distance from here to here, is 24 feet. We see that the change in this distance, meaning change of the base of the ladder from the wall, is 7 feet per second. We also know at that snapshot in time that y, which is this vertical distance here, we'll kind of move it back up here. Yeah, this vertical distance here of the ladder is going to be 7 feet. And we also see here that since we know what x is, and we know what the length of the ladder is here, that we see that how we're actually finding y. So that's what all this work here is for, okay? So the problem initially gave us this information and then this information, and we can find out what y is. Of course, we know that this is a popular triangle here, where this is a 7, 24, 25 right triangle from geometry. But just in case you did not know that, this is how this is worked out. The other thing that you see here is that I'm noticing, according to my variables with respect to time here, if they're positive or negative, okay? So going back up at the model, you'll see here that the height of the ladder on the wall with respect to the ground is a function of time, because as the ladder slides further, the base of the ladder slides further and further away, the ladder's height gets less and less and less. So because of that, we know that this vertical height of the wall is decreasing, which means that it should be negative. The angle that is in between the ladder and the wall is also decreasing, and the area is also decreasing. And so the reason for that is that there's part 2 of this problem that asks us at what rate is the area of the triangle formed by the ladder, wall, and ground changing. So, and then we also have a part C to this as well, where at what rate is the angle changing. So that's why I'm doing all that. Okay. So for part A, let's scroll back up. We see that what is the rate of change of the height of the top of the ladder? So the top of the ladder is modeled by the function y of t. So we're basically trying to find dy over dt. So as you see here, we set up everything according to Pythagoras Theorem. And we see here that whenever we take the derivative of both sides with respect to t, of course this right side is 0. The left side, we do the chain rule. And so we notice that since we have a specific value for x, a specific value for y, and we also have what dx over dt is, because we know that the base of the ladder is increasing at a rate of 7 feet per second, we can plug all that stuff in to our equation. And then the one thing that we're trying to find out, which is what is the rate of change of the height at the top of the ladder, that is rate of change of y with respect to t, which is here. That's what we're trying to find. So we substitute everything in, and you see after we do the computation, we get a negative 24 feet per second. Now moving on, we want to know at what rate is the area of the triangle formed by the ladder, wall, and ground changing. Okay, so we know that here area is 1/2 times the base times the height. So we know that. And so when we look here, we want to take the derivative of both sides of this equation. Since we want to know what is the rate of the area, we're trying to find the change in area over time. So of course this will be a is equal to 1/2 the base times the height. So if we take the derivative of both sides of this equation with respect to t, then it starts off looking like this, where the base is characterized by x and the height is characterized by y. And so you see that when we do this, both x and y are assumed to be functions of t. So what that means is that we have two functions being multiplied times each other, and we want to take the derivative of it. So we're going to use the product rule in that case. So we took derivative of first times the second plus derivative of second times the first. And then from that point, we see that dx over dt from what we knew earlier. Let's go back to that. So our dx over dt here is just 7 feet per second. We also see that we know specifically what x is and what y is at the time. So we're given that x is 24 feet, and we found out that y is 7 feet. So of course we plug all that information in, and then the last thing is the dy over dt. We found that in part A, so we're able to plug that in here. And so with all that being substituted in, we go and solve for the derivative of area with respect to t, and you see that we come out to have the area decreasing at about 263.5 square feet per second. So that's mighty fast. And so for the last part, what we now want to do is figure out how fast is that angle changing. Okay, and so here what we notice is that, of course, going back to our model here, you'll see how I have cosine of theta is equal to x over 25, which is the same as 24 over 25. But we know that because of what was given to us in our problem. And so here we're just saying cosine of this angle is just adjacent over hypotenuse. And that's what we're doing here. And of course you see that I've calculated that in degrees as well as radians, what the actual angle is at that specific time. May not necessarily need that, but it's just there just in case you want to use it. So if we look here, we see that we have an equation here, and if we want to find out the derivative or the rate of change of the angle with respect to time, then of course we have what we need inside here. So if we take the derivative of both sides of this equation, when we take the derivative of cosine theta, since the variables do not match, we have to use the chain rule. Okay, and so on the right side, of course, variables don't match again here, so we end up having to use the chain rule again. And so on the left side, we see that cosine theta, the derivative of that with respect to t, is just derivative of the outside function, negative sine theta, times derivative of inside function, d theta over dt. We also see that dx over dt, whenever we take the derivative of the right side, of course, variables still don't match. So we have to take the derivative of x divided by 25, which is just 1 over 25, for the outside function, times derivative of the inside function, which would just be, sorry, I'm pointing in the wrong place here, which would just be here, the dx over dt. And then, of course, we plug that information in. And so now from there, we come and we try to solve for d theta over dt, which is just 7 over 25 divided by a negative sine of theta. And of course here, the approach I took when I worked this out was to just kind of plug in this information here. But really, I didn't have to do that. If I go back to my setup here, we know that since this part of our triangle here, the x is 7, then I know that sine of theta is just going to be, let's put that in the wrong place. So the 7 should be here and the 24 should be here. So we know that sine of theta should just be opposite over hypotenuse, which is just 7 over 25. So, and looking at it that way, once we come back down here, instead of doing what I did here, all I had to do was come here and say, all right, well, this is just 7 over 25. And since this is negative, we do that and we get -1 for our answer. All right, so with our next example, we see we have a person that is on a dock and they're pulling in some small boat. And so we see here that the rope is being pulled in at 3 feet per second. And if we know that, we want to know how fast is the distance between the dock and the boat decreasing when it is exactly 30 feet from the dock. Okay. So as you can see here, I've sort of tried to model this to where we see that the system in between the rope that we have here, the distance in between the boat and the dock, and how far up this person is holding the rope from the floor of the dock models a right triangle again. And one of the things that we do here to make sure that we're very clear on what is what, we say that x is the distance between the boat and the man, and we say that y is the distance in between the boat and the dock. Okay, so put another way, x is going to be the length of the rope as it changes, and of course y again is the distance in between the boat and the dock. And of course, as this person pulls in the rope, we know that the length of the rope is going to decrease. Okay, so if we look at that, if we say what is the change in the length of the rope, or the length in between the distance of the person and the boat, that should be less than 0. And so because of that, this is why we have here that dx over dt should be negative 3 feet. And if you notice here, if we go back up to the problem, you see here how it says the rope is being pulled in at 3 feet per second. There is not a negative showing up in the problem, but if we interpret this system correctly, we know that it has to be negative. So that's why that negative 3 feet per second is there, okay? Now, of course, we also see here that the change in the distance in between the boat and the dock is exactly what it is that we're looking for here. Because it says how fast, or that's another way of saying at what rate is the distance in between the dock and the boat decreasing. And so we know that this dy over dt, which is the rate in which the distance in between the boat and the dock changes. We also know if it's decreasing that this answer here should also be negative or less than 0, okay? Now, we also note here that from our system, of course, the x, the y, and the 4 feet here model a right triangle, so we can use Pythagoras Theorem again. And so we see here that, of course, if we're talking about the distance between the floor of the dock and the person holding the rope, that's just going to be 4 squared here. The distance in between the boat and the dock at the time that we're looking at it is 30, so that's why you see 30 squared here. And x squared is, of course, that side that represents the length of the rope. And so in looking at this, we know that 4 squared is 16, 30 squared is 900, and if we solve for x squared, we get x is equal to 2 times square root of 229, okay? And of course, we're only considering the positive part of this answer here, because really this is plus or minus, but we're only considering the positive part because length cannot be negative. So now that we have established this, we can actually go back here and use this system again, modeled as the relationship of Pythagoras Theorem. And here we can take the derivative of both sides of this equation here with respect to t. So if we do that, then of course this is what it looks like. And so here we know that with y and t, the variables do not match, so we use the chain rule, as you see here. And so that's y, when we take the derivative of y squared, we would get 2y times dy over dt. Of course, whenever we take the derivative of 16, derivative of any constant is 0, so that's why we have that there. And of course here, x and t do not match. So when we take the derivative of x squared with respect to t, it would just be 2x times dx over dt. From here, we know that dx over dt is -3. And what we also know here, we haven't plugged it in yet, but we know that y is going to equal 30. And of course, there's a corresponding value for x that goes with that too, which is this 2 times square root of 229. So if we keep going here and plug in this information, we see that once we do it, we see that the change in the distance in between the boat and the dock is decreasing at a little over 3 feet per second. And if you remember, the person that's on the dock pulling in the boat, they're pulling it in at a rate of -3 feet per second. So what we're seeing here is that as this person pulls in the boat closer to the dock by the rope that's attached to it, the distance in between the boat and the dock is decreasing a little faster than it takes for the person to pull it in. Okay. So we have one more example to go through. So for this next example, we see that we have a point that's moving on the graph of this ellipse, and we know that when we're at the point 3, 0, its y coordinate is decreasing by 2 units per second. Okay, and so that's why you see dy over dt, meaning the y coordinate is decreasing by 2 units per second. And we want to know how fast is the x coordinate changing at that moment as well. Okay. Now, what is implied here is that the y coordinate is a function of time, in other words, seconds. So that's why we have the dy over dt here. And so x is assumed to be a function of t, and y is also assumed to be a function of t. So this is why when we end up taking the derivative of both sides of this equation with respect to t, we will have to do it implicitly by employing the chain rule. Now, the info that we're given again, the y coordinate is decreasing by 2 units per second. So that means the rate of change of y with respect to t has to be negative. We also know that at this particular point, 3, 0, that x is 3, y is 0. And dx over dt, which is how fast is the x coordinate changing at the moment when a point moves to this location of 3, 0, that's actually what we're trying to find. So now that we have all that collected, we see here all we have to do is take the derivative of both sides of our equation here. And this is just the equation of the ellipse. So if we take the derivative of both sides of that with respect to t, then as you can see here, variables don't match, so we use the chain rule. So derivative of 4 times x squared with respect to x is just 8x. But the derivative of x with respect to t is just dx over dt. So this part here forms the 8x. And of course, the inside function x here, derivative of that with respect to t is just dx over dt. Same thing with 9y squared, taking a derivative with respect to t. Of course, we ignore the constant here, and we just say the derivative of y squared with respect to t is just 2y times dy over dt. And then, of course, the derivative of any constant is 0. From that point, we just do a little cleanup and get to this point here. And then we know at this point right here, we're saying that when x is 3 and when y is 0, what is going to be what dx over dt is, okay? Now, if we look here, we also have dy over dt, which is going to be a -2. So here, I'm going to go ahead and put this in, but we're going to see that this really doesn't matter. So we can put that in. And so it doesn't matter because, again, y is equal to 0. So when we do that, we could have this -2 that's in here, but 0 times anything other than infinity is just 0. So we're just dealing with this term here, which ends up being 24 times dx over dt. And we see that our x coordinate here with respect to time is not decreasing at all. And of course, you probably thought, well, yeah, that kind of makes sense since it's on the x-axis. At that particular moment, it's not increasing or decreasing at all. So not exactly what's going on, but it just turns out that at that particular moment, that is what's happening. Reason being, if we look at it, if we come back and look at this relation here, rather, if we just looked at 1/2 of this and we looked at this as x in terms of y, just looking at this half here, right at this point, of course, there's a vertical tangent line there, but if we looked at it as x in terms of y, it would be a horizontal tangent line. And so we know that at peaks and at dips, the rate of change is equal to 0 at those places. So that's kind of what this particular question is communicating to us. So with that being said, this concludes our discussion on related rates. which is just another way of saying word problems where we use implicit differentiation. I hope this video has helped. If you have any comments or need any clarification, just make sure to comment. Thank you so much for checking this out.